Hey, this is Mr. Boyce, and we are continuing our video series prepping for final. Today, we're going to do Unit 10 and 11 combined. This one's going to go a little bit quicker than some of the previous ones. So let's go ahead and get started. So these first few, these are really just sort of vocabulary things. You can look these up, so I'm not going to spend a lot of time on this, but according to the law of thermodynamics, heat can be transferred from one substance to another. So T-S-E-R-O, thermodynamics. Okay, so next we have different types of energy. So energy of motion, that's going to be kinetic. And if I spell something wrong, we'll just have to get over it. Energy is stored in an object due to its position. This is potential energy. A form of kinetic energy resulting from the motion of particles and is transferred as heat. This is thermal energy. And then finally, a form of potential energy related to the structural arrangements of atoms and molecules. So this means that there is energy in bonds, and the breaking and forming of bonds is what causes that transfer of energy. So this is chemical potential energy. Chemical.
Hello, Wildcat Workout Group. Coach Jordan is going to be meeting everyone in the large gym today. The elbows.
Okay. So in a beaker, substance A reacts with substance B to produce heat. The reading in the thermometer in the beaker increases. Describe the energy transformation from the above. And so pretty much with all transfer of energy, you're always going from a higher energy to a lower energy. And so in this case, the reading thermometer in the beaker increases. So what that means is that the water is increasing in temperature, and therefore the reaction is releasing energy into the water. Uh, and so therefore this would be thermo. So, but always higher energy to lower energy. We're going to cover that again because that's a very important concept. Okay, classify each as endothermic and exo. So some of these get a little bit weird, and some of them can almost be a little debatable depending on how you look at it. But solid KBr is dissolved in water, and the solution gets colder. So remember, you always want to think of yourself as the system, and the system is the solid KBr that's dissolving in the water. The water is the surroundings. And so if the surroundings get cold, that means that the system had to have gotten energy, and it's got to get it from somewhere. So it took it from the surroundings. So therefore, this is endothermic because the system is taking energy from the surroundings. A furnace works by burning natural gas. Well, that's a combustion reaction, which is very exothermic. This one's pretty easy. A sample of water is boiled to produce steam. So instead of going back and forth and thinking, what, I don't know what to do, just think about before and after. So a sample of water is boiled, which means it started as water and became steam. And which one has more energy, steam or water? Well, steam has high and water is low. So if I go from lower energy to higher energy, that means I had to absorb energy. So therefore, endothermic. So you don't want to think just this turn hot, did this turn cold. You want to think more about where you started and where you went to. Okay, a reaction forms products with less potential energy than the reactants. So, in other words, a reaction lost energy. It went from having more energy to less energy. So, this would be exothermic. And a reaction recurs and the water temperature drops rapidly. We kind of already talked about this. If the water temperature is dropping, that's because the reaction is taking energy away from it. And this is endothermic. Okay, energy diagram. These ones are kind of easy, and a lot of people lost a lot of points on these, which kind of sucks. So let's talk about this. Is the reaction endothermic or exothermic? Well, it doesn't specify forward or reverse reaction. So if it doesn't, you can usually just assume that's forward reaction. And if we start off on the forward reaction at 400, that's what's right here. It's a little hard to read. And then we end up at 200 right there. And so if I start at 400 and I end up at 200, that means I lost energy. So exothermic. What is the value of delta H or enthalpy for the forward reaction? Now, this is one a lot of people missed on the test. Forward reaction. So delta is always final minus initial. So in this case, for the forward, my final is 200 kilojoules minus my initial, which was 400 kilojoules, and 200 minus 400 equals negative 200. So negative 200 tells me that this is exothermic, is losing energy, but this is the answer to the question, is negative 200. What is the enthalpy for the reverse reaction? Well, once again, final minus initial. So I'm just going to reverse this to 400 minus 200, and that's going to equal a positive 200. So this system is gaining energy and therefore endothermic. EA, so this is energy of activation. So remember, energy of activation, it's not as simple as just looking and saying like, oh, okay, this point right here is 500. You have to look at where you started. That's why it's different from forward to reverse. So in other words, if I want to buy something that's $100, I've already got 80 bucks in my pocket. I don't need 100 bucks. I need 20 bucks. Same thing here. So energy for the forward reaction. Well, for the forward reaction, I'm starting at 400 and I need to get to 500. So I only need another 100. So for the forward, I need 100 kilojoules. For the reverse reaction, I'm starting at 200, right? And to get to the energy of activation, I need to get to 500. So final minus initial, 500 minus 200 is 300. And so for the reverse, I am going to need to find 300 kilojoules, search in the couch somewhere. Which would proceed faster, the forward reaction or the reverse reaction? Well, obviously the forward is going to take a lot less energy than the reverse action. So that one is going to proceed faster because you're going to get to that energy of activation first. Forward, whoops. Forward we move. If a suitable catalyst was added to the reaction mixture, what would change? Describe the changes. So a catalyst, remember, is a spectator. It doesn't really change the products or reactants or anything. But what it does do is it lowers the energy of activation requirement. And that's going to be true for forward and reverse because we needed energy in both cases. So if you reduce that energy need, you're going to speed up the reaction on both sides. Okay, let's get to these ones here. What is the enthalpy change for the following reaction? Now, again, I've got a delta, and if I see delta, I'm not thinking change, I'm thinking final minus initial. If you're feeling uncomfortable with these, take the slightly longer but much more foolproof way of just writing this reaction in reverse. Remember, it's the sum of the n times your values, final minus initial. And in this case, this all balances out to 1, so this one's kind of easy. But I'm going to write this reaction kind of in reverse. I'm going to write CO plus H2O plus N2 as my final minus my initial of CH2N2 plus O2. And then from here, what I'm going to do is just sub those symbols out with numbers. And that's going to be here. Again, I don't have any, it's balanced all at once, so I don't even have to worry about coefficients. So I'm just going to put negative 110 for CO because that's what's there. Water, they're even in order. Plus negative 285.9 plus N2 and N2 here. That's 0. So I don't really need to worry about that. So let's just take that plus away. And there we go. Minus initial. Now my initial, I do have here the CH4N2. So minus, and this is a positive, so 62.4 plus O2, and O2 is also zero. So remember, delta H is formation, and you don't have to spend energy to form something that's already in its most elemental state. And oxygen is diatomic, so O2 counts. So this would be a pretty simple one. I'm going to let you put this in the calculator. Put negative 110 plus negative 285.9 subtracted from, so put that in one in parentheses so the calculator knows that that's, you want the total of the final minus the initial. So let's move on. We're gonna skip way ahead. Okay, this one here, this is gonna be a little bit more work, not a ton more, but a little bit. And so same thing, final minus initial. Now you don't have to write out the whole equation, so I'm not going to do it this time. I'm just going to write out what I see here, but I'm going to do it in numbers. So I'm going to start with this. AL203, do I have a value? I do. It's negative 1676. I've only got one, so negative 1676 plus, remember, because that these are pluses here, right? Like we're basically rewriting this formula, final minus initial. So plus ALCO3, again, I only have one of those, so negative 704 plus next is NO. So here it is, and that's at 90. But most importantly, got to pay attention to this. I have three of them, all right? Three of those, and I have 6 oxygens. That's super important. So plus parentheses 3 times my NO value of 90 and close parentheses. So that way your calculator knows what you're talking about. Plus, and then I've got 6 H2Os. Here's my H2O value. So plus parentheses 6 times negative 242, close parentheses. And I'm going to go ahead and put a parentheses around the whole thing. All right. So that way my calculator knows this is all one thing. And whatever the answer for this one thing, I want to subtract from that my initial right here. Okay. And I have a feeling I know what aluminum is. Yep, it's 0 because it's already in its elemental state. So minus 3 times, again, this 3 super important. NH4ClO4, where you at, buddy? Right here, negative 295. Make sure I didn't write that anywhere else. Okay. Negative 295. Close my parentheses. And so there you go. You put that in the calculator. It's going to give you an answer. My answer was somewhere in the neighborhood of negative 3,200-ish. You need to come up with the specific answer in order to get credit. In fact, let's just go ahead and go back up here. And in here, my answer was, whoops, somewhere around negative 450. But again, to get credit, you need to have an answer somewhere around there. So make sure you do. Unless, of course, I put it in the calculator wrong, which if I did, tell me. Okay. Now let's move on to this chart. This is also super important. So from point A to point F, the sample is going through, and this is a multiple choice, which is great. And what's happening, temperature and energy is going from lower to higher overall. And so this is gaining energy. So endothermic versus exo, gaining endothermic. So I can rule out A and B because this is not exothermic. Now, if it said F to A, that's different, but it didn't. So this is endothermic. And does that mean it's releasing heat into the surroundings, or does that mean that it's absorbing heat? Well, endothermic by definition means that I am absorbing heat. So there you go. What's happening between points D and E? It's very important that you understand what's happening between all of these points. So here, let's just make some numbers up that are somewhat true. Let's say negative 30 Celsius for here. Let's just say 0 because this is my freezing point. And here, let's give that a value of 100. All right, so there. And then let's say, I don't know, negative or not negative, positive 120. Why not? All right, that looks about the scale. Okay, so from negative 30 to 0, water is ice. From 0 to 100, it's water. and anything above 100 is steam. Okay, and again, this is asking about B to D, but I'm just going to kind of, or I'm sorry, D to E, but I'm just going to kind of keep going. So what's happening between A and B? Because your question could ask any one of these, so why not just know them all? So between A and B, let's put a red highlighter. This is when you're going to use your Q equals MC delta T math because you want a change in temperature. And so this is going from -30 to 0, and this is a delta T. This is a change in temperature. Same thing here from C to D. This is changing from 0 to 100. So whether you go all the way from 0 to 100 or 0 to 50 or whatever, you're going to use Q equals MC delta T to find out how much energy that change in temperature took. And then finally from E to wherever that ends up, steam can get pretty hot. Either way, still equals Q equals MC delta T. Now here, this is what it's more asking about, B to C. What's happening here and what's happening here? These are phase changes. And what's happening is, notice that the temperature isn't changing during the phase change, but the amount of time, and assuming you're putting the same amount of energy in the whole time, the amount of time marches on, but the temperature doesn't go up. And that's because I want you to imagine here at 0 degrees Celsius, when I first hit 0 degrees Celsius, I've got a big old block of ice, and I've just now gotten to the temperature where it could possibly start to freeze. It's not going to freeze like that. It's going to take energy. I hope that snap doesn't sound too loud on the video. It's going to take some energy to go all the way from ice to water, even though you are at the proper temperature to do it. And so that's a phase change. This is your delta H of fusion. And then up here, your delta H of vaporization. This is how much energy it takes to go from water at 100 degrees Celsius to water, or water at 100 degrees steam at 100 degrees Celsius. So right when it first starts to steam. And same thing with the ice cube, right? Like if you put a pot of water on the stove and it starts boiling, it's not going to instantly turn into steam. It's going to take some time to transfer all that water into steam. It's going to take time. It's going to take energy. And so this is a phase change. This is when it's going from water to steam. All right. And there you go. So no matter what two blocks they ask you about, you'll be able to nail that question now. That's great. During condensation, gas turns into liquid. What happens to the energy during condensation? Well, let's look at it this way. You've got gas and you have liquid. And what has more energy? Gas has high and liquid has low, at least in comparison, right? And so if you go from high energy to low energy, what is happening? Are you absorbing energy? No, you're not. You're going from high to low, you're losing energy. And that means, there you go, energy is being released. It's not being absorbed. It's certainly not being created or destroyed, because that's one of our big rules, is that energy cannot be created or destroyed. So those options are almost kind of meant to be a joke. Okay, this is the last one for that. Wow, this is going to be a pretty quick video. So this is the last question. I added this in here because I really, really want to make sure that you understand this concept. So a hot slice of pizza is put into the refrigerator according to thermodynamics. Which of these statements are correct? A, heat is transferred from the warm pizza to the lower energy surroundings. B, the surroundings transfer cold to the pizza. What you probably thought your entire life is a reasonable thing to think. You put something in there, the refrigerator makes it colder. That's not really what's happening as far as chemistry and thermodynamics happen. You're always going from higher energy to lower energy. So in other words, that high energy pizza is releasing heat into the surroundings. The colder surroundings is absorbing that heat. Now, in the case of a fridge, you keep pumping more cold air and eventually you'll reach a equilibrium point. But if you unplug the fridge and you put something hot in there, then this rule makes a lot more sense. It's going to warm the fridge up if I put hot stuff in there. So remember, you're always going from higher energy to lower energy standards. And if you see questions that are asking things like that, that's how I want you to think about these things. And you will do great as long as you remember that. Okay, up next will be acids and bases. So I'm going to go ahead and cut this off because it's already 2 units. And then I will see you again in acids and bases. So thank you. If you have any questions, be sure to ask.